The next technique that we are going to learn is called trigonometric integrals. That might not really be the technique, but just the kind of integral we're going to attack. And generally speaking, this is a combination of using identities for trigonometric functions and substitution. So first you manipulate the integral using some kind of identities, often the Pythagorean identities, and then you're able to do a u substitution as a result. But first, let's start off, since we only spent one day on integration by parts, let's review that technique, which is sort of a basic example. So remember that the integration by parts formula is that the integral of u dv is equal to uv minus the integral of v du. So here, we're going to let u equal ln of t. We'll let du equal, well, du will then be 1 over t dt. dv will be t to the 1/2 dt. And v will equal the antiderivative of t to the 1/2. You take the power and you add 1, that's 3/2. And the coefficient is now 2/3. Even though you technically know how to antidifferentiate ln of t, it's easier to integrate this function this way. The other way may work, but I'm pretty sure it's just like leads you down a black hole of pain. So this integral is uv, so 2/3 t to the 3/2 ln of t minus v du. So I'm just going to take that 2/3 out right away. So minus 2/3 antiderivative of t to the 3/2 times 1 over t dt. And t to the 3/2 over t, those exponents subtract, reducing to t to the 1/2. So we have 2/3 t to the 3/2 ln of t minus 2/3 times the antiderivative of t to the 1/2 dt. So 2/3 t to the 3/2 ln of t minus 2/3 times the antiderivative of t to the 1/2 is 2/3 t to the 3/2, and then plus c. And of course 2/3 times 2/3 is 4/9. So your final answer is 2/3 t to the 3/2 ln of t minus 4/9 t to the 3/2 plus c. If you got that, beautiful. Now today's technique is different. As I said, it's a combination of trigonometric sort of manipulation with identities and substitution. So first let's review some integrals where substitution works to kind of get an idea for what happens. So here we have sine of x to the 5th power, that's what that little 5 means, times cosine of x. So if you were to let u equal sine of x, du is cosine x dx. Now the point being, whenever you let u equal sine, you have to save a cosine to take care of the du. But once you get that, this integral reduces to something quite simple. You just have the that pen doesn't want to write. You just have the integral of u to the 5th du. And that's super simple. So 1/6 u to the 6th plus c, or 1/6 sine to the 6th x plus c. Not a problem. So the point being, if you make your u a sine, you have to save a cosine. If you were to make your u a cosine, you have to save a sine. Of course, in here that makes no sense because cosine is only one cosine, there are multiple sines. So here's another one, some different functions. So here the substitution to make is for tangent. Let u equal tangent of x. And the reason you choose that is tangent's derivative appears in your integrand. The derivative of tangent is secant squared. So du is secant squared x dx. And as long as you can see the substitution, this simplifies down quite nicely to the integral of u to the 7th. And the antiderivative of u to the 7th is 1/8 u to the 8th plus c, or 1/8 tangent to the 8th x plus c. Now our goal with today's examples, or today's sort of technique, is to reduce our integrals down so that we can make substitutions like these. Many of those reductions will involve using these Pythagorean identities. So this first identity is the most basic trig identity, and you really should know this one. It effectively is the Pythagorean Theorem. I'll just show you for the first quadrant. So on your unit circle, you should know that the circle has radius 1, and the horizontal distance given an angle is cosine of x, and the vertical distance is sine of x, if x is the angle. And then you see just a triangle. It's a right triangle, hypotenuse 1. So the Pythagorean theorem says that sine squared plus cosine squared is 1. That is where this first identity comes from. All right, now the second and third ones come from this identity. If you take this expression and you divide everything by cosine squared x, sine squared over cosine squared is tangent squared, cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. To derive the last identity, you take the original and you divide by sine squared x. Sine squared over sine squared is 1, cosine squared over sine squared is cotangent squared, and 1 over sine squared is cosecant squared. You are going to have to memorize those, so figure them out. I think that the tool that I gave you is the best way to remember them. Memorize the first one, which is just the Pythagorean theorem, and then memorize how to get the others. Now, cosine cubed x. So notice that a regular substitution for cosine won't work here, so we cannot, right in regs is wrong. You can't let u equal cosine of x because your derivative is sine x, and there's no sine x to take the place of du, so this is not going to work. X nay that idea A. So the technique here is to use the identities to manipulate this so that you can do a substitution for maybe a different trig function, say sine, because sine's derivative is cosine. A little bit like there's no signs there. What am I going to do? So here's how you proceed. Write cosine cubed x as cosine squared x times cosine of x. This thing is going to be saved to be your du. Your goal is to let u equal sine. Now you know that sine squared x plus cosine squared x is equal to 1. So that tells you that cosine squared x is equal to 1 minus sine squared. So you have the integral of 1 minus sine squared x times cosine of x dx. And now notice that you can let u equal sine, and if you do, du is cosine of x. And this integrand simplifies to the integral of 1 minus u squared du. And that's something that you can handle. The antiderivative of 1 is just u. The antiderivative of u squared is 1/3 u cubed plus c. And insert your substitution. We have sine of x minus 1/3 sine cubed of x plus c. And the general strategy is if you have an odd power on a sine or cosine, you take one of them off, save it, and change the rest into usually the function you're trying to make a substitution for. If both the powers on sine and cosine are odd, you can kind of go either way and there's more than one equivalent answer. So here we have sine to the 5th times cosine squared. So if I'm going to use the Pythagorean identities, I have to make the power on the sine even by taking off a sign. So the first step I'm going to do is write this as sine to the 4th x cosine squared x times sine x dx. And the singular thing that I'm saving is going to be my du. So my goal for u is to let u equal cosine. So u is going to equal cosine x, and du will equal negative sine of x dx. So negative du equals sine x dx. And the way you get these patterns is you just do lots of practice and just try some stuff. And now you're like, well, so this is just going to be replaced by u squared, but that's sine to the 4th. There's no identity for sine to the 4th, but actually there is. If you think about sine to the 4th as sine squared x times sine squared x times this cosine squared x, we're going to leave them alone because that's what we're going to substitute for, sine x dx. Okay, so sine squared is 1 minus cosine squared. Since I have two sine squareds, what I have here is the integral of the quantity 1 minus cosine squared x, the quantity squared. And at this point in time, the only sign I have left is the part that's going to be taken care of by the du, so we're just going to now we're going to substitute. So the negative, I'm just going to stick out in front, negative integral 1 minus u squared, the quantity squared, times another u squared, du. And it's tedious, but you can do it. So next step, take this 1 minus u squared quantity squared and expand it. So 1 minus u squared times 1 minus u squared, and we have negative integral 1 minus 2u squared plus u to the 4th times u squared. I'm going to do two things at once. I'm going to distribute the u squared and the negative sign. You can not do the negative sign if you would like to skip it, but either way, just make sure that you keep track of it somehow. So we have the integral of negative u squared plus 2u to the 4th minus u to the 6th. And most of these examples will reduce something super easy when you make the right substitution. So this becomes negative 1/3 u to the 3rd plus 2/5 u to the 5th minus 1/7 u to the 7th plus c. And then substitute in what your u was, then you have negative 1/3 so we have negative 1/3 cosine the 3rd x plus 2/5 cosine to the 5th x, and then minus the 7th cosine the 7th x plus c. Now when the powers on sine and cosine are not odd, you can't use the Pythagorean identities because you'd end up having to sort of replace something that was an odd power, and the Pythagorean identities only deal with even powers. So in that case, you use these half-angle identities, and it is the case that you saw these in a trig class, but actually in a different context. So I'm just going to show you where you probably saw them. You probably saw this as multiplying the half over 2 sine squared x equals 1 minus cosine of 2x, or 2 sine squared x minus 1 equals negative cosine of 2x, or cosine of 2x equals 1 minus 2 sine squared x. I'm sure there's a good reason. I'm not sure why they show you only that way and not the other way, and maybe they did and it's been a long time, but this is the way this is what we're going to use most frequently. And notice what happens is that the angle x is doubled. So if that were 4x, if this were 4x, this would be 8x. If this were 10x, this would be 20x. All right, let's show you how those work. So you have the integral from 0 to pi of sine squared of x. So that's the same thing as the integral from 0 to pi. So sine squared x is 1/2 times 1 minus cosine, the angle doubles, becomes 2x. And that 1/2 can just factor out of the integrand. So we have 1/2 the integral from 0 to pi, 1 minus cosine of 2x. And now, pretty simple integral. So we have 1/2 times x. All right, the antiderivative of cosine is sine, and then we'll have to have a 1/2 because of the 2x, so minus 1/2 sine of 2x evaluated from 0 to pi. So now plugging in pi, that's 1/2 times pi minus 1/2 sine of 2 pi minus 1/2 times 0 minus 1/2 sine of 0. Now sine of 2 pi is 0, sine of 0 is 0, so all we have here is pi over 2. You can also, and actually really have to, apply this technique to something like sine or cosine to any even power. It won't work to break it into sine cubed x times sine x because there is no way to change those sine cubes all into cosines because the Pythagorean identities only involve even powers. So that method's no good. But you can express this as the integral of sine squared x, the quantity squared, or sine squared x times sine squared x. And we know that sine squared x is 1/2, 1 minus cosine of 2x. Note the double parentheses and be careful, everything is squared, including that 1/2, which squares to 1/4. So I'm going to also pull that out of the integrand. So 1/4 integral. Now squaring 1 minus cosine of 2x, we get 1 minus 2 cosines of 2x plus cosine squared of 2x. And I'm looking at that expression, this is good, this is good, this we still have to mess with. Quite similar to the last example, except for it's cosine instead of sine. So we have 1/4 integral of 1 minus 2 cosine of 2x. Now cosine squared of 2x is the same thing as 1/2, 1 plus cosine of, now the angle doubles, it was 2x, it becomes 4x dx. And once you get that, it's pretty easy cheesy. Now notice that when this 1/2 distributes, we're going to have 1 plus 1/2, which makes 3/2. So 1/4 integral of 3/2. It's easiest to combine terms before you anti-differentiate. Minus 2 cosine of 2x, and then plus 1/2 times cosine of 4x. Okay, so 1/4. The antiderivative of 3/2 is 3/2 x minus 2. The antiderivative of cosine is sine, so sine of 2x times 1/2. And the antiderivative of cosine is sine. Again, we're going to need a 1/4 there, so 1/2 times 1/4 sine of 4x. And then don't forget that plus c. Be ashamed to miss that now. Plus c. Let's just do a little bit of simplifying and then we're done. So you have 1/4 3/2 x minus sine of 2x, and then plus 1/8 sine of 4x plus c. And as you can imagine, if you had sine to the 6th x, you have to do sine squared, sine squared, sine squared. It'd be really tedious, and I probably wouldn't do that to you. Sine to the 4th probably is the worst that will happen. Similar is technique for 2 plus sine, the quantity squared. So when you expand that expression, you end up with the integral of 4 plus 4 sine of theta plus sine squared theta d theta. And the first two terms, no problem, but that last term you have to use the half angle identities to change it into 1/2 times the quantity 1 minus cosine of 2x. So before we integrate, this is 4 plus 4 sine theta plus 1/2 times 1 minus cosine angle double, so it was theta, now it's 2 theta d theta. Now when we distribute that 1/2, we have 1/2 plus 4, and in calculus, fractions are pretty, mixed numbers are kind of ambiguous. 4 and 1/2, if you input that into WebAssign, it's not clear if it's 4 plus 1/2, which is what it is, or 4 times 1/2. These are different answers. So it's really best to have improper fractions. 4 plus 1/2 is 8/2 plus 1/2, which is 9/2. I mean, you can even say 4.5, that's fine, but 4.5 is not great notation. I'm not sure why that's emphasized so thoroughly in elementary school, but x nay the mixed numbers. Plus 4 sine of theta, and then minus 1/2 cosine of 2 theta. Okay, so the antiderivative of 9/2 is 9/2 theta, plus antiderivative of sine is, let's think negative cosine. So 4 times negative cosine of theta. Of course, you could have made that a subtraction sign. I just already had the plus written down, so that's how I compensated. And then minus 1/2 times another 1/2 sine of 2 theta, and then don't forget that plus c. So your final answer is 9/2 theta minus 4 cosine of theta minus 1/4 sine of 2 theta plus c. All right, you pretty much have exhausted the options with sine and cosine, so just keep track of those even odd powers thing. Now we have tangents and secants. So you have to think, if I u sub tangent, the derivative of tangent is secant squared, so you have to save a secant squared to be your du. So think the goal in your mind is you're going to let u equal tangent, and then du will be secant squared x. And this works if the power on the secant is even, because then you can save secant squared to be your du, and the other secants can be converted into tangents using the identity, let's write it in the exact same order as you had, tangent squared plus 1 equals secant squared. So that's, we're going to use this. So first of all, this is equal to the integral of tangent to the 6x secant squared x times secant squared x dx. And these we're going to save. The other secant squared we're going to replace with tangent squared plus 1. So this is the same thing as the integral of tangent to the 6x times tangent squared x plus 1 times secant squared x dx, which becomes the integral of u to the 6th times u squared plus 1 du. And by then it's pretty simple. We'll just distribute your u to the 6th. You have the integral of u to the 8th plus u to the 6th du. And the antiderivative of u to the 8th is 1/9 u to the 9th. And then plus 1/7 u to the 7th plus c. If you want to anti-differentiate and also plugs your u back in at the same time, that's not a problem. So our final answer is 1/9 tangent to the 9th x plus 1/7 tan to the 7th x plus c. So obviously on this example, if you think about it, what we just did won't work, because if you let u equal tangent, you got to save a secant squared, and here that will leave secant to the 5th. And the Pythagorean identity that we have, you have to have an even power of secant to change it, so that's not going to work. So we let u equal tangent in the previous problems is a bit more tricky, but if you let u equal secant, let's just recall for a second. If u is secant, recall that the derivative of secant is secant tan. So if your end goal is to let u equal secant, you have to save a secant and a tan to be the du. And let's just look at what happens when we break it up and sort of pull off one tangent and one secant. We get the integral of tangent to the 4th x secant to the 6th x times secant x tan x dx. So these are on reserve. They're already taken to be the du. If your u is going to be secant, the things you want to change is that tangent to the 4th. And recall that that's tangent squared the quantity squared. So tangent squared x, the quantity squared, times secant to the 6th x times secant x tan x dx. So that tangent squared x. So we know that tangent squared plus 1 equals secant squared. All right. And if that's the case, well then tangent squared is equal to secant squared of x minus 1. So you have the integral of secant squared x minus 1, that quantity squared, secant to the 6th x times secant x tan x dx. And let's make our substitution. We have the integral of u squared minus 1 quantity squared, u to the 6th, and that secant tan is just your du. And so now it's just a little bit tedious algebra. So u to the 4th minus 2u squared plus 1 u to the 6th, or u to the 10th minus 2u to the 8th plus u to the 6th du. Now just to save some time, I'm going to both anti-differentiate and plug back in my substitution. So the antiderivative of u to the 10th is 1/11th, u to the 11th, and u was secant of x, so 1/11th secant the 11th x, minus antiderivative of u to the 8th is u to the 9th over 9, so 2/9 secant to the 9th x, and then plus 1/7 secant to the 7th x plus c. Occasionally, you can do the integral both ways, as in you can let u equal secant, or you could let u equal tangent. Sometimes that works, and we'll have an example where that happens. The same is true for sines and cosines sometimes. All right, so in this one you have two options. You could have your goal to be u is cotangent x. In that case, du would be negative cosecant squared x. But proceeding with that route, you would have to save cosecant squared, and you'd have a singular cosecant, which you really can't manipulate because the Pythagorean identities involve cosecant squared. So that's probably not the way to proceed. The other option is to let u equal cosecant of x. In that case, du is negative cosecant x cotangent x dx. So you have to save a cosecant and a cotangent. So let's just sort of start this process. This is the way to go. So we have the integral of cotangent to the 4th cosecant squared x times cosecant x cotangent x dx. So that's being saved. And if your goal is to substitute u for cosecant, you've got to change these cotangents into cosecants, which you can do using the identity that 1 plus cotangent squared x equals cosecant squared x, and therefore cotangent squared x is cosecant squared x minus 1. And so that cotangent of to the 4th x is the same thing as cosecant squared x minus 1, the quantity squared, times cosecant squared x times cosecant x cotangent x dx. And then make your substitution. So because du is negative cosecant x cotangent x, we've got to add a negative sign out in front. We'll have u squared minus 1 squared times u squared du. And you can see there's just lots of this. Once you identify how to make the substitution, the resulting integrand should be pretty simple. So negative expand u to the 4th minus 2u squared plus 1 times u squared du, negative integrand u to the 6th minus 2u to the 4th plus u squared du. And once again, I'm going to integrate and plug my substitution back in. So we have negative 1/7 cosecant to the 7th x. I'm going to say plus here because that negative distributes, cosecant to the 5th x, and then minus 1/3 cosecant cubed x, and then plus c. And just to measure, let's do one where you actually let u equal cotangent. So you can see that the power on cosecant is even here, and that's kind of what the kicker is, what matters. So u is equal to cotangent x. And in that case, your du is negative cosecant squared x dx. So we break this up. And we're going to say we're going to have a cosecant squared x. We have to change, but we can do that because we have an even power on the cosecant. Cotangent to the fourth x, that's going to get substituted for, times cosecant squared x dx. That part's saved to be your du. And cosecant squared x, using the Pythagorean identities, that is equal to 1 plus cotangent squared x. So we've got 1 plus cotangent squared x times cotangent to the fourth x times cosecant squared x dx. So we have the integral of 1 plus u squared times u to the fourth. The cosecant squared x dx is replaced by negative du, so negative du, or negative antiderivative u to the fourth plus u to the sixth. And your final answer is negative 1/5. So the antiderivative of u to the fourth is u to the fifth over 1/5 u to the fifth. Plug back in cotangent, 1/5 cotangent to the fifth x plus 1/7 cotangent to the seventh x plus c. Negative can distribute or not. Now the last thing, one of the last things today, is the sum difference formulas. Now these you do not have to memorize. No memorizing. I just expect you to know that they exist and use them when appropriate. So I'll have an example that makes it really, really simple. The alternative method is to actually use integration by parts and the around the world trick, but this is significantly simpler. It takes a product, notice it takes products and makes them into sums. Products, hard to integrate. Sums, easy, hence useful. So you have sine times cosine, sine times sine, or cosine times cosine. This is what you use. So we have, in this case, sine times cosine. So using that formulas, we have, this is the integral of 1/2 times sine of 4x minus 5x. Notice that a is the angle inside the sine function and b is the angle inside the cosine function, plus sine of 4x plus 5x. And so we'll just take that 1/2 out. We'll have 1/2 integral sine of minus x plus sine of 9x. And one identity that you should know, I'll write this on the side in different color just so you can keep track of it, is that Sine x is an odd function. And what that means is that when you plug in negative x, it's the same as negating sine of x. So, for example, plugging in pi quarters, so sine of negative pi quarters is the same as negative sine of pi quarters. So that lets us take this and pull the negative out of that sign. And sine is an even function. Cosine of x, sine is odd, cosine is even, and that means that cosine of negative x equals just plain old cosine of x. So you may have to use those things. So we'll have 1/2 times the integral of negative sine x plus sine of 9x. And other than that even oddness business, this is now quite simple to anti-differentiate. The antiderivative of negative sine is just plain old cosine, and the antiderivative of sine of 9x is negative 1/9 cosine. Almost made a mistake there. Negative 1/9 cosine of 9x plus c. And if you feel as if you want to challenge yourself, you could try integration by parts and see if you can make this work. It's going to be an around the world kind of thing and take a lot longer, but you could just see if you can make it happen. Now, something else that might be useful, there are some formulas that you might have to use and you're allowed to just sort of use them. I'm not going to make you memorize them, but it is pretty useful to know where they come from. So about the first one, let's just mention a couple things. So first thing is, why did I say or? These are equivalent, and let's explain why. So negative ln, absolute value of cosine x, using rules for logs, that's the same thing as ln of cosine x, absolute valued, to the negative first power, which is the same thing as ln of 1 over cosine x. And by there, hopefully you can see it because 1 over cosine is secant. So that's ln absolute value secant x. So that's why you can give that formula either way. Now, where that formula comes from, the first one's pretty easy to figure out. Most of you have done this before. You think about tangent as sine of x over cosine of x. And you do a u substitution. You let u equal cosine, and your du is negative sine. Most of you should be able to work that out from there. That one isn't very hard to derive. The second one is legitimately quite tricky, and honestly, I wouldn't remember it unless I taught calculus for the past 10 years in a row. The way you derive this, and I wrote the wrong thing, so let's fix that. The way you derive this is you take your secant of x and you multiply it by secant x plus tan x over secant x plus tan x. And while it isn't immediately obvious why in the heck you would do that, is at least obvious that it's true, that that's not, you haven't changed the integrand at all, because secant x plus tan x over secant x plus tan x is just 1, and multiplying by 1 doesn't change anything, so no big deal. So take your secant x and distribute, and you get the integral of secant squared x plus secant x tan x over the denominator of secant x plus tan x dx. And now if you substitute for the denominator, which is why you did this whole thing in the first place, you get that the derivative is secant x tan x plus secant squared x, which is the quantity that is in your numerator. So that is so tricky to derive. It cannot appear on a quiz or test in my opinion, but it might appear on your homework because I haven't vetted those problems, and I assume that you can use your notes if you run into trickery. So that's where they come from. This is a little bit about why they are what they are, and you can finish the integral to prove to yourself that that is what happens. But that's a hint that should get you started.